New York City's Citibike bike share system is the largest in the country, with over 800 stations and nearly 2 million trips made every month. With such a huge system in such a large city, rebalancing becomes a formidable task, making machine learning algorithms that can predict demand and allow more efficient rebalancing activity all the more valuable. To address this issue, we use predictive modeling to develop an algorithm and design an app for bike rebalancing in New York City's bike share system. This map shows the distribution of Citibike stations in New York City in blue and Jersey City in orange. We focus on stations in New York City for the purpose of this model. An inherent challenge in operating a bike share system is the uneven distribution of demand and the resulting difficulty in ensuring the availability of bikes or docks for users where and when they need them. To cope with this, bike share operators manually redistribute or rebalance bikes based on spatial and temporal demand trends. This map illustrates this asymmetrical distribution of demand. Green dots represent stations that had a higher demand for bikes, which in turn represents the origins of people using Citibike. Pink dots, on the other hand, represent stations with a higher demand for docks, corresponding with people's destinations. In the AM peak, there tends to be an excess of bikes in job centers like the financial district or Midtown, meaning that people are traveling to these areas from their residences in other parts of the city. The trend flips in the PM peak as people return home to areas like the Upper West Side and Lower East Side. To address these issues, we introduced the new and improved Citibike app. The app will have two use cases, one for operators who will be redistributing multiple bikes at a time in special vehicles, and the other for customers who can redistribute bikes in exchange for points and perks. This is the operator view. Operators can see the number of bikes to be redistributed to or from each station based on the model's predictions. Higher priority stations are marked based on predicted demand in the coming hour, and stations are differentiated based on which ones need bikes picked up and which ones need bikes dropped off. The operator version also has routing capabilities, which help the operator efficiently redistribute bikes to and from the highest priority stations. This is the user view. It presents a gamified version of the operator view, where bike demand and station rebalancing priority are translated to reward points that users can gain by redistributing bikes. Higher points can be gained from higher priority redistributions. Points are tied to members' accounts through the Bike Angel program, which is a way that Citibike currently incentivizes customers to redistribute bikes in exchange for perks like extended memberships. So what does the model behind this app look like? Based on the requirements of this app, the model needs to provide three main features. The first consideration is supply versus demand. The model has to determine whether a station has too many available bikes or too many available docks. The second consideration is the rebalance number, which, along with the supply versus demand consideration, is calculated from the model's predicted demand minus its predicted supply. In other words, this represents the excess demand for bikes based on the predicted departures from the station minus the predicted arrivals. If this value is positive, supply of bikes is higher than demand and we need to remove bikes. If the number is negative, demand for bikes is higher than supply and we need to add bikes. Finally, the priority score incorporates the rebalance number as well as an adjustment for the amount of activity that a particular station has at a given moment to reflect the immediate need for rebalancing at that station. We can determine both supply and demand using predictive regression models. Because most stations have small trip counts for each hour, mostly less than 10, we used 100-fold Poisson regression to build the model. We built two models, one predicting arrivals, which corresponds to the supply of bikes, and one predicting departures, which corresponds to the demand for bikes, hourly at each station. We subtracted the supply from demand to obtain the predicted number of excess bikes at each station for each hour of the day. Our model used data from the second week in May 2018 as the training set, and the third week in May as the test set. Predictive factors used included spatial and temporal autocorrelation variables, including the ridership numbers from neighboring stations, as well as values from corresponding time periods the previous week and previous year. Other factors considered include job and residence distribution, weather patterns, and physical features such as bike infrastructure and slope. When we dive deeper into the model and examine the individual folds created, we can see that the model appears to have predicted somewhat consistently over 100 random folds. These two graphs represent mean absolute errors across all 100 folds for both models we develop, with the arrivals or supply model on the left and the departures or demand model on the right. However, when we look closer, some inconsistencies emerge and we can see that the model is less generalizable over different variables. These graphs represent the average predicted bike demand and supply across all stations for May 25th. While the predictions roughly followed the trends of the actual values, we can see that error values fluctuate over time, with the model particularly underpredicting during the AM peak and overpredicting during the PM peak. This reveals that there is some level of temporal autocorrelation that remains unexplained by the model. Looking spatially, this map shows the average error values for the same time period across all stations. Here we can see that the model tends to have higher errors in its predictions for stations around Midtown Manhattan, with errors seemingly decreasing the further a station is from this area. This reveals that there is some level of spatial autocorrelation as well that remains unexplained by the model. Based on these results, there are a few ways we can try to improve the model further. We can introduce even more predictive factors to try to explain the remaining variation. We can develop a model that directly predicts the excess demand for bikes rather than deriving this prediction from two separate models. And finally, we can expand the model to take into account the current availability of bikes and docks. When combined with predicted excess demand values, this will allow the model to meet the predictive needs of the app and convey information on how many bikes are projected to be available throughout the day.